All right, we're going to be looking in section 3.5 on our rational functions and their graphs. So we continue with this idea of functions and kind of assessing what their graphs look like and how to be able to transition those and transform those all over our axis system. So we're also going to get in kind of our horizontal asymptotes. We looked at some vertical and horizontal asymptotes we're going to see in here, and also kind of look at some different notation that we use whenever we are analyzing the behavior of a graph. So let's get started. Rational functions are quotients of polynomial functions, and so they can be written of a form where, if you remember, rational numbers are those that are fractions. Now we just change numbers into functions, and we have a rational function. Okay, but here we have to designate where P and Q are polynomials, and we have to make sure that we realize that Q of X is not equal to 0 because we cannot divide by 0. So, as a reminder, the denominator of a fraction, here it is, cannot equal 0. So let's practice finding the domain again of these rational functions, which we've done multiple times. So hopefully you're kind of mastering this idea of finding the domain. The domain is described to be a place where the denominator is 0, and we're extracting out those x values because they are not allowed in a rational function. So we can always look at the denominator and set that equal to 0 if we want, and then extract out that number. So this one's kind of obvious. What do we subtract 2 from in order to get 0? That answer, if you were to add 2 to both sides, would be x equaling 2. Now, not sure exactly the way that my lab math is going to ask for your answer, so we've seen it both ways. I'm going to write it both ways for you. So I want all the set of x such that x is not equal to 2. And then we can also do interval notation where I start at negative infinity, I go to 2, I skip over 2, and I have to have those parentheses representing that that's not equal to at that point. So either way will work. Again, I'm not sure exactly how my lab math will ask you for an answer. All right, so we turn to the next one, and I pop in an x squared in there. Anytime we have a squared polynomial, remember that is a possibility that we could factor that in order to figure out what two answers will make that equal to 0. So if I see x squared minus 4, remember that is one of those differences of squares that we have. One is a plus, one is a minus. We make sure that we distribute our x in a sense, or split it up and give 1 to each of those. And we ask ourselves, what do we multiply by itself to get 4? And the answer is 2. Therefore, now instead of just having one answer that makes that 0 like we do over here, we actually have 2 answers that make that true. And so 2 is actually another one of these roots that would make that equal to 0. And this one, for what number plus 2 gives me 0, that would be negative 2. So in set notation, we would say we want all x such that x is not equal to negative 2. And then separate it by a comma, or you can put and x is not equal to positive 2. So that would be in our set notation. As interval notation, we would start at negative infinity, get to negative 2, and skip over that. So we have to end up doing this idea. Going from negative 2 to positive 2 would give me this interval, and skipping over that positive 2 to infinity would give us that idea. So again, either one of these will work. You just have to make sure you remember how to find what makes that denominator equal to 0. Now, on this last function, we have x plus 2 over x squared plus 4. Notice all this time before, I've not even worried about the numerator. I haven't even said the numerator in those previous problems. So we want to make sure that you just work with the denominator when you're working with domain. So the question would be, what would make this guy equal to 0? Obviously, yes, we could set that equal to 0. And if I solve that, I get x squared equal to -4. And so we ask ourselves, what do we square to get a -4? Well, remind yourselves, we're working in the real numbers here when we're working on these coordinate planes with functions. And so this is actually an imaginary answer. So if you think about that, there is no number that you can square to equal -4 in the real numbers. Or look at it this way. Is there any number that I square that when I add 4 gives us 0? Well, anytime that you square a number, you get a positive number. And when I add 4 to that, you're going to get an even more positive number. Therefore, that will never equal 0. So the domain of this function is going to be the set of all reals, or in interval notation, you can go from -infinity to +infinity. So be very careful. There's a big difference here between a plus in there and a minus in there when you're working with domain. All right, so the rest of our discussion in section 3.5 is going to be working with graphs and their axes, asymptotes, and all that kind of stuff. So we're going to talk about two of the most basic rational functions. One of them being f of x equals 1 over x, and the other one being f of x equals 1 over x squared. Okay, so we're going to look at each one of those and determine what its graph looks like. And then we're going to be able to kind of move things around to transform it like we've done before in other situations. So I'm going to start with the first one. F of x is equal to 1 over x. And what we can do, just by like any other graph, we could do a t-chart if we wanted to figure out what does it look like and what points that I have. So I'm going to start with -3, -2, and go all the way. Actually, I'm going to undo that one. -3, -2, -1. I'm going to go -1/2, 0, 1/2, 1, 2, 3. So I'm doing a little bit more points in here just so that you can see kind of the behavior of that graph, just because if I do a couple of the integers, it's not going to be very nice to see. All right, so if I have -3 and I plug that in for x, I end up getting a -1/3. If I put in -2, I get a -1/2. If I put in -1, 1 over -1 is -1. Now the question would be, what would happen when I get 1 over -1/2? Well, remember, this kind of in a sense gives us the idea of a reciprocal, or it's also the division. When I divide by a fraction, and I have to multiply by the reciprocal of that. So I would get 1 times a -2 over 1. So in this case, I get a -2. So really, the 1 over is asking for a reciprocal. Now, if I have 1 over 0, that can't happen. So that's going to be undefined. 1 over this 1/2. Again, what is the reciprocal of this? It would be +2. What's the reciprocal of that? +1. Reciprocal of 2 would be 1/2, and I get a 1/3. These are pretty obvious. When you plug them in, you get 1/2 and 1/3. All right, so if I graph these points, at -3, I get -1/3. So it's going to be really, really small. At -2, I'm at -1/2. At -1, whoops, sorry, I'm not in the negative, so let's revert back. Let's undo that. So -3, let's go below for the -1/3, excuse me. -2, -1/2, -1, -1. If I'm at -1/2, I'm at -2, so I'm approximately here. At 0, it's undefined. There's nothing that can happen there. So for this point, I'm going to do a dashed line there. And we'll talk about that in just a second as a vertical asymptote. And I'm going to plot 1/2, 2, 1, 1, 2, 1/2, and 3, 1/3. So we have graphs that look like this, okay? And in the end, it's going to look something like this, where, in the sense as I get going to -infinity and +infinity, those numbers are going to get really, 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 really small. So if I have like -100, I'm going to have -1 over 100, which is going to be really, really, really small. I'm never, ever, ever going to ever get this equal to 0, because in order for a fraction to equal 0, the top has to be 0. 0 over any number is 0. Well, I'm never going to have that in this function. So I'm never going to actually equal here at y equaling 0. So I'm going to do that, and we're going to talk about each one of those as being horizontal and vertical asymptotes in these types of functions. But I want you to kind of get the idea of what that looks like, okay? Now, let's turn our attention to the f of x equals 1 over x squared function. And when I do that, again, it's nice to kind of see a t-chart at the first whenever you do that. And I'm going to choose the same numbers. And when I plug those in, the only difference is now I have to square the denominator. So when I square the denominator, when I put -3 in and square it, I get 1/9. Put -2 in there, I get 1/4. Notice both of those are positive. All of these are going to be positive because when I square any number, I get a positive number. When I square the -1/2, I get 1/4. But when I take the reciprocal of that, I end up with 4. Again, we have an undefined at 0. We're going to have a 4 here, a 1 here, a 1/4, and a 1/9. So in a sense, it is symmetric. If we check our symmetry properties where I throw -x in here and -x in here, I would end up coming back to the original function. Hence, it's an even function being symmetric over our y-axis. Okay, again, at 0, I'm undefined, so I'm going to go ahead and kind of put that number or that dotted line in to represent the asymptote. When I graph at -3, this is at -1/9, so just to get as kind of close to that axis as you can. At -2, we end up having -1/4. Then I have a positive 1, not a -1/4, positive 1/4. So we're at -1, positive 1, -1/2, positive 4 will give me that answer. Then again, we have undefined at 0. At 1/2, we're at 4 as well. Then we're at 1/1. Then we're at 2/1/4. And we're at 3/1/9. Okay, and when I look at that graph, again, the idea is looking somewhat similar. But we now have first and second quadrants versus first and third quadrants. And again, we are going to just be approaching this y equaling 0. Again, we can never equal 0 when I just have a number on top. It has to be 0. So these are the two graphs that we have for 1 over x and 1 over x squared. These are the only ones we're going to kind of look at with rational functions. Now, we will never touch these axes. So you just approach them. They never will cross them, okay? And that's what kind of leads us into our next idea here, where we're going to get some notation about what happens on these functions whenever we are approaching a number from a certain direction, whether we're approaching positive or negative infinity, etc. So a lot of times you will use this type of notation in calculus when you're talking about limits. So I have this, and this means is x goes to some number a from the right. So as x approaches a from the right is the way I could read that. If I have a notation where I put a minus kind of in the exponent, that means we're looking at x approaches a from the left. If I end up looking at x going to infinity, that means that x approaches infinity. And if I throw in a negative there, obviously then x approaches negative infinity. Okay, so we're going to have to kind of scroll here a little bit because my problems that I have here are looking at the graphs above. So here, we're looking at a certain function, and I'm asking what happens to the y value as x approaches a certain number. So this one is, as x approaches 0 from the right, what happens to my f function? So we're going to kind of look at the behavior of our graph here. So as x approaches, here's x equaling 0. Or you can kind of think of it on the axis here. Where is x equaling 0? It's right here. So go on your function, and to the right of 0 would be on this side. I'm going to kind of travel along my function, and what happens is it gets very close to 0. Well, my function keeps going up and up and up and up. And if I choose like 10 or 1/10, which would be here, then I would be up here at 10. What happens is that we grow we grow to infinity here. As I approach 0 from the right, I go to positive infinity. So that's what I want to put on my function here. That would be at positive infinity. Now, what happens as x approaches 0 from the left? What happens to my function? Where does it approach? So we're going to go on the other side of 0. On the left-hand side of 0 is this way. Grab a hold of your function. What happens to that function? Well, it keeps going down, 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 down to negative infinity. It's going to go there forever and ever and ever. So our answer here would be, as x approaches 0 from the left, our function value goes to negative infinity. Now, what about this guy? Here it says, what happens when x approaches infinity on my function? What happens to the y value or the function value at that point? Now, x going to infinity, that's positive infinity. So it's looking at what's happening to the behavior of the graph as far as I can go out here. And again, traveling along my function, what's going to happen is that that function value is going to just approach that 0. It's never going to cross 0, but it's going to go towards 0. In essence, we call that limiting towards 0. So the answer here would be 0. Okay? Now, we end up having our 1 over x squared function that we now kind of do the same idea, except for here we're going to look at negative infinity. But what happens as my x value goes to 0 from the right? So I'm going to find x equaling 0, grab onto my function as it comes from the right. What happens to my function? Well, it keeps going up and up and up and up and up to positive infinity. So that would be my answer here. So it's the same as before, but not always. What happens is x goes to negative infinity of my function. So we come up here, we go, did I say x go to infinity? What I'm going to say what happens is x goes to 0 from the left is what I wanted to say. Okay, so here's x equaling 0. To the left of 0 is on this direction. So as I'm approaching 0 from the left, my function keeps going up and up and up, again to positive infinity. And the last question here would be, what happens as I travel to negative infinity? What happens to that function value? So we're going to go out as far as we can go on the x value. What happens as we go to negative infinity out here? Well, again, it's never going to cross this horizontal asymptote, but I'm going to get very, 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 very close to 0. So again, if I had 1,000,000 that I plugged in into my function, I square that 1,000,000, and I get a very large number. 1 over that's going to be a very, 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 very small number. So this is going to be 0 as well. Okay, so just a little bit of notation there. Those aren't too bad once you kind of get the directions going on, but it is good to learn that in case you do move forward in a sense with your mathematical courses. All right, so let's talk about these asymptotes that I alluded to, vertical and horizontal asymptotes. So I'm going to say that the line x equals a is a vertical asymptote of a graph of a function f if the function value f of x increases or decreases without bound as x approaches a. So what do we mean by without bound? That means they're going to infinities, okay? So they're going up and up and up, or approaching 0 to infinity as it goes there. Now, any vertical asymptote occurs where the denominator is equal to 0, aka these are the numbers which are restricted from the domain, and we've done that numerous times. We just now need to say x equals that number, and that's going to be our vertical asymptote. So when we were doing that at the top, this is going to be a vertical asymptote. These two on this graph would be vertical asymptotes on that, okay? So we're just going to get one vertical asymptote. We're not going to go as far as to graphing some of those other rational functions. So graphically, what does it look like, okay? So if I end up having something that looks like this, and I have a function here with that, a vertical asymptote could be one that is going here. So if I call this a, as x approaches a from the right, then I have it going to positive infinity. It's increasing without bound. We could also have another function that in a sense is going like this, and I have a vertical asymptote right here. Call that at x equaling a. We would have that again increasing without bound right here. Now, if I wanted to go to negative infinity, you might have a function that kind of looks like this. And we have a vertical asymptote right here where we're just approaching that at negative infinity. And we could also have that kind of coming from the other direction where I have a function that looks like this with a vertical asymptote as it approaches there. So all of these would be at x equaling a. And so that's kind of your different scenarios that you can have with the vertical asymptote. So as x goes to a from the right, or as x goes to a from the left, then our f of x is going to approach plus or minus infinity. Basically, that's kind of what we're working with here. Okay? All right, very good. So, in the basic graphs above, what we have, I'm kind of alluding to this next statement here, in the basic graphs above, the vertical asymptote in each is the line. So let's look here. Where's our vertical asymptote for each of these? We have it here and here. That is the line x equaling 0. That's that vertical line x equals 0. Or we can also think of it as the y-axis. Okay? All right, so looking at these functions, which are very similar to the other ones that we had before, notice here that I have, and we're going to add a piece here where I need to make sure that I have everything simplified before I denote an asymptote, okay? So for this first one, this is x squared minus 4. We just alluded to that on the other side as a difference of squares, so it would end up factoring like this. There's actually nothing that we can do to simplify here in that original function. So both of these are going to be vertical asymptotes. What makes this 0 is negative 2. And what makes this 0 is positive 2. So x equaling negative 2 and x equaling positive 2 would be our vertical asymptotes. Now, in this one, it's different because now I have a numerator of x plus 2. When I factor x plus 2 and an x minus 2 for that difference of squares, these are the exact same factors. So we could actually cancel those out. Now, you're still going to be restricting out negative 2 out of your domain, but for it to be a true vertical asymptote, if things can cancel, you want to cancel those first, and then whatever remains, the function now would look like this. Whatever remains is going to kick out a vertical asymptote. What's going to happen at this point right here, there's just going to be kind of a skip in the graph at negative 2 if we were really to analyze that. So again, when finding rational functions, simplify the function first and then determine what's left over. So here, the only vertical asymptote is going to be where x equals positive 2 because that's what makes that 0. Okay, so a little twist on that. Now, if we look at this function, where is this x squared plus 4 equal to 0? Well, we talked about that, where if I square a number and I add 4, it's never going to equal 0. It's always going to be positive. When I add 4, it's still going to be positive. So there is no asymptote here. Okay, so it's okay to not have any vertical asymptotes. So you may want to say this is not equal to 0 ever, so that you have that. Okay? All right, very good. So the vertical asymptotes are kind of a little bit easier because you worked with domains so much to kind of identify. Horizontal asymptotes are ones that you kind of have to think about and know some of the rules in a sense. Okay, so I'm not going to get into too much of why it is or how I can find it because there's a calculus component to this and you guys don't really need to know that. So we're just going to look at the most basic way of finding a horizontal asymptote. So I'm going to say that the line y equals b is a horizontal asymptote of a function f if our f of x approaches b as x increases or decreases without bound. So we're going to be approaching a specific number as we go to positive infinity or negative infinity. So what does that look like? I could have a horizontal asymptote of y equaling b here, and I could end up approaching that from here, and this guy right here means that we're increasing with that bound as x gets bigger, okay, and we're approaching that b, so this would be y equaling b. I can also have one in a decreasing function where I'm decreasing down and then we start approaching. Here, this would be y equaling b. And I also have like a little twist here. If I let this be my function, vertical asymptotes you cannot cross, but horizontal asymptotes you actually can. So if I end up crossing and then I come back up here like this and I end up kind of approaching that value, then you end up having a horizontal asymptote that cross, okay? But, so can cross horizontal, but not vertical. Okay, very good. So now there's 3 different ways to determine what is the horizontal asymptote, and it all is dependent upon the highest power in the top and the bottom. Okay, so remember those are kind of like the degree of our polynomials. So if the highest power in the top is less than the highest power in the bottom, so you have like an x squared over an x cubed, then the horizontal asymptote that we have for that function is going to be the line y equaling 0, and you can also recognize that as the x-axis. So if you look at kind of this guy up here, this power is 1, this power is 2, that is the degree of those. This would actually have a y equals 0 horizontal asymptote, okay? And so making sure that you can recognize those powers. Now, if the highest power on top and bottom are equal, this is where the most work occurs. Then the horizontal asymptote is found by dividing the coefficients or the numbers of the highest powered terms on top and bottom. And we'll see that in just a second. Now, if the highest power on top is greater than the highest power on bottom, then F has no horizontal asymptotes. Those are what we call slant or oblique asymptotes when you end up having that. So if you wanted to write that just as your extra information for this lesson. Those would have that type of asymptote. So we're not going to get into that, but it does occur. All right, so we're going to find the vertical, find the horizontal as an asymptote. I just noticed that was incorrect. So we're going to find the horizontal asymptotes, if any, of the graph of each rational function. So here, we're designating the power on top and the power on bottom. So here, our powers are equal. So we got to go back up here to this one and say, okay, if the powers are equal, then we do have a horizontal asymptote, but it's found by dividing the coefficients of the highest power. So here's my highest power, here's my highest power. What we want to extract out are these numbers in front of there. And we have to divide those. So when I do 9 divided by 3, I do get a 3. Therefore, y equaling 3 is the horizontal asymptote for this function. Okay, so you have to know the rules to be able to do that. So here, the degree is 3, and the degree is, 2. So we have the top being greater than the bottom. So therefore, I come up here to part C, and if I have the top being greater than the highest power, then there is no horizontal asymptotes for that function. Okay, and that's possible. We have a possibility of no vertical asymptote. Now we have a possibility of no horizontal asymptote. And this last one, here I have a power of 1, here I have a power of 2 is the highest power of those. The top power here is less than the bottom power, which reminds me that I need to go up here to part A. And if that does occur, then we are given that the x-axis or the line y equaling 0 will always be that horizontal asymptote. Okay, so make sure that you are able to work with those. I will do that and say that if you just have a number up top, so if that was just 9 or something like that, then the degree of a constant, if you remember, is 0. So this power basically on top would be 0, like if I had something like this guy right here. The power on top here, the degree would be 0. The degree here is 1, so 0 is less than 1. Therefore, y equaling 0 is going to be my horizontal asymptote here as well. Okay? All right, very good. So let's see what happens in this function. These are going to be some transformations of the different functions that we've seen. Remember what 1 over x looks like. 1 over x was that function where I was in the first and the third quadrant. And so now we're going to kind of look at, okay, what happens to this function if I have an x plus 1 in the bottom. Notice here I have a plus 1 at the end. So just like before when we were working with our x squared functions, our square root functions, anytime it is grouped with the x, that means we have a horizontal shift or an x shift. So we have to take the opposite of what we're looking at. So this original function where I have an asymptote at x equaling 0 and a horizontal asymptote means on this one we are going to move to the left by 1. There's a horizontal shift of the left by 1. So now my vertical asymptote at x equaling 0 is going to be at x equaling -1. So remember those transformation ideas because we're not done with them just yet. Now here again you can plug in values. We're at x equaling 0. This would be 0 plus 1, but if you remember kind of over here, this is a power, you know, you get at the point 1, 1, we were at the point 1, -1. You could kind of look at some of those points on the very front side here. I'm talking about these. And once you shift it, you can end up doing these points that we have here. Okay? So if you remember them, that's fine. If not, nothing says that you can't just plug in a value. Okay? So here we 1/2 we would be at 2. Then we went over here like 1/2. Get a couple points there and just kind of sketch it. I'm sure you're probably going to have to be looking at some graphs on your paper or on your computer screen and then assess and pick which one it is. Okay, so this would be the graph of our 1 over x plus 1. Now, moving on to this, we have 1 over something plus something. So this is going to take on the idea of that 1 over x function. But here, now I'm grouped with the x. I have an x minus 2. Take the opposite of what I'm looking at. We're going to move to the right by 2. And because I have this plus 1, that means we're going to move up 1. That's our vertical shift. So if you remember, we had, you know, like an x squared function. We ended up saying x minus 2 plus 1, and I have that part squared. This would be the same thing where I'm moving to the right 2 and up 1, but now I have to have a parabola as my shape as opposed to this 1 over x. So if I move to the right by 2, that vertical asymptote now moves to the right by 2. And if I move up 1, then that is going to also now be my horizontal asymptote. So you can kind of treat this as your new axes, but in this function, they are actually asymptotes. So if I go over 1 and up 1 from that new origin, in a sense, I would have that point. I would have this point. Go over 1/2 and up 2. Go over to 2 and up 1/2. That's going to create that rational piece there. And if I likewise do that over here, -1/2 from the new origin down to 2, and -2 down to -1/2. So being familiar with those points will be helpful. Okay, and again, you may have to actually plot some points. You may just need to have to assess the graphs of which one matches with that function. Okay, now this one, the last two, are working with the function 1 over x squared. So if you recall, and actually I forgot to say this earlier, but some of my students would refer to this as the Atari function for some of you that like to game. Way back when I was young, had an Atari because the symbol looks like an Atari symbol. Google it if you don't know what it looks like. But now if I look at this, I have 1 over something squared. So it is going to take on the graph of that 1 over x squared function. So we are now in the first and the second quadrants. I have a vertical asymptote at x equaling 0. Oops, a horizontal asymptote. What's going on? Okay, a horizontal asymptote at y equaling 0, but now we're going to turn on some shifts. So if I'm grouped with that x, we're going to have that horizontal shift. So this, take the opposite of what I'm looking at. We're going to move to the left by 3. When I do that, now I have that vertical asymptote at x equaling 3. I stick with my horizontal asymptote at y equaling 0, and I now have these points. Now remember, we're at 1, 1, and at 1/2 we were at 4. over at 2, we were at 1/4. So we end up kind of having this graph in a sense where we're just approaching that y equaling 0. And if I mirror image that because of my symmetry on the opposite side, I end up getting something that looks like this. So those over 1, up 1, and in the corresponding quadrant is the key point that you have on these. Okay, so that would be my graph for 1 over x plus 3. Now this last one here, again we're taking on the 1 over x squared idea because I have a square now. I have a shift to the right of 1, and this is my vertical shift of down 2. So I have right 1 and down by 2. So if I go to the right by 1, that new vertical asymptote is at x equaling 1. If I go down by 2, my new horizontal asymptote is at y equaling 2, and that's kind of acting as my new axes. So if I, from my new origin, go over 1 and up 1, I get the point 1, 1. I can also have the point on the other side of that. At 1/2, remember we're up 4, 1, 2, 3, 4, so we would be here. I'm again going to mirror image that on the other side of that asymptote. And at 2, from the new origin, we would be at like 1/4. So I'd have a point about there, and then on the other side about there. So again, here we're just kind of sketching them on my lab math. They may ask you to kind of look at those and figure out which one matches, or also may have to plot some points as well. But nothing says you can't always put in these numbers into that function to figure out where that point occurs. Okay, so that's what we have for our rational functions in section 3.5. We are going to actually move now into section 4.1 and dealing with some exponential functions. So I think we've got 2 more functions to go with graphing and such. And we're going to hit the exponential function and the logarithmic function. So until next time.